The next topic that we'll talk about is sensors and interaction between the device and the real world. As we recall from the discussion on embedded systems, we saw that embedded systems do not reside in isolation. The embedded systems are there in order to be able to interact with the real world, to get feedback from the real world, and then to be able to cause something to happen in response to the feedback. How does the embedded system learn about what is going on in the real world? It needs to gather information from the real world. And the way it does is making use of sensors. Now, what kind of information can you gather from the real world? Any examples of information that you can gather from the world around you? Sorry? Voice. Voice is not sound. That's what it is. Sound. What else can you gather from the real world? Temperature. Yeah. Today you walk outside. You are an embedded system. You walk outside and say, "Oh God, it's so hot." How do you know it is hot? Because you have sensors, right? That's the other one. Temperature. What else can you gather from the real world? What more information can you gather? Sorry? Picture. Oh, you mean visual information. Let's use the real term, the correct terms. Visual information. So you are able to gather visual information. Visual information could be gathered in the form of truly, something that is visible to the naked eye using a camera, or you could use infrared sensors. Infrared sensors could be used for gathering information like distances, or gathering information like infrared sensors for looking at the temperature. That's one possible way. What more can you gather from the real world? For example, think about yourself. If you walk outside, depending on where you are, what more can you say about your own information?
Smell.
Sorry? Smell. Yeah, smell. Yeah. That's true. Yeah. Sense of smell is also a piece of information that you can get. You could have a smell-based embedded system. I don't know what to do with it, but you could easily have a smell-based embedded system. So there are applications for that you can easily think of. Like, for example, you could have an embedded system that is detecting leakage of chlorine gas, for example, if you're storing chlorine gas in containers somewhere, and then you're detecting leakage. Similarly, if you dig mines, for example, you're detecting for methane gas in there. That's one more piece of information that you can gather. You have forgotten some of the most important things that you could think of. A sense of direction for me. Which direction am I facing? North, south, east, or west? Right? How do you gather this information? Like if you're put it right in the middle of somewhere, how would you be able to tell whether you're facing north, south, or east, or west?
Compass.
You don't know? Compass. If you don't have a compass, how else can you gather this information? Look up at the sky. There is something going on the sky there, right? If it is a daytime, of course. If it's a nighttime, it's a different matter. If it is daytime, you know that based on the position of the sun and based on the time of the day, you can approximately guess which way north is, which way south is, and so on. Right? So, direction. Another kind of information that you can very easily make use of. Orientation. Similarly, for a device, for example, pieces of information include things like acceleration. How do you gather acceleration? Suppose you throw your phone up into the sky, and then it is falling down. It is experiencing a certain acceleration. So that's one thing that you can. Now, obviously, you don't want to throw the phone up the sky, but there are places where you can easily sense this. Like I'm sure you have done this, right? You move your phone like this. How many of you have played with the Nintendo Wii controllers before? You have played? You have played? How do you use it? You move your hand like, I have never seen one myself, but I believe this is what you do, right? You move your hand.
No, it's not like it's not that good. I think.
It's not.
You have it. It's like there's a receiver, and then you can only move like this.
Yeah, within a limited.
Yeah.
Within a limited. Yeah, because it's only a question of gathering the information. So it's not that it is because within a limited budget you can only put certain things into the device, right? If you pay only $10 for that, obviously the sensor that you can put there has to be less than $1, right? Otherwise it is not profitable. But in a smartphone, for example, you get a lot of sensors that are already built in, right? Any one of you having smartphones easily realize that you have sensors that are primarily dedicated to motion, position, and orientation. Why is this important? Well, if you use a tablet or a phone, you do notice that if you hold the phone vertically, the screen will be in one way. The moment you flip the phone in another direction, the screen automatically changes its orientation, right? How does the phone realize that you're holding the phone in one of two different ways? That information is gathered based upon these sensors. Okay? Similarly, ambient environment around you, things like temperature, brightness. How is brightness used in a mobile phone, for example? Can anybody think of an application for brightness in your mobile device? One very natural way that you can think of brightness?
You will automatically change the brightness of the screen according to the environment brightness.
Exactly. Brightness of the screen can be adjusted based upon the ambient brightness. If you wake up in the middle of the night and you look at your phone and your phone screen is very bright, it is very distracting. So you want it to be a lot less, a lot more softer on your eyes. But in bright sunlight, you want your screen to be very bright so that you can read the screen. So adjusting the brightness based upon on the light amount of light that is surrounding the device. Auditory and visual, this is what you refer to, sound and microphone, to be able to gather information. Now, all these pieces of information could be very effectively leveraged to perform many different kinds of tasks on your device. Okay? Now, this is what distinguishes writing applications for mobile devices as opposed to writing applications for your standard computers and laptops. How many computers do you have that have accelerometers built in? 0. How many computers do you have with compass built in? 0. There is no need for them. Obviously, you're not going to be carrying your laptop and walking around. And I've seen people doing it, but it's dangerous to do it. But mobile devices are a lot more portable. And obviously, you want them to be used in ways that are different from your standard computers. Within your computer also, there are places where you have sensors like accelerometers built in. Can you guess one place where an accelerometer is included in your computer? How many of you know about this? Never heard of it? How many of you know that your hard disks, especially if you pay a little bit more money for buying a hard disk, hard disks have accelerometers in there. Why? Because by chance, if you drop your device, if your hard disk hits the ground strongly, it can easily, I mean, not even that much. If you drop it from this height onto the table, it can cause you, if your hard disk is actually doing some work, it might end up scratching the head of the disk platters on your hard disk, and that will lead to disk crash. the moment you detect that your device is falling, you want to be able to immediately stop the head movement and then put it in a safe position so that your hard disk can be saved. So many hard disks, a bit more expensive hard disks, come with tiny accelerometer sensors built in there that can detect, to protect from some amount of faults. Obviously, if you drop it from the top of floor down to the ground, you can't expect your hard disk to, your computer won't survive, first of all, let alone your hard disk. Okay? But minor jerks for which you can avoid disastrous consequences can easily be arranged by using hard disks. Okay? But mobile devices obviously come with a wide array of sensors, and they can be very easily leveraged for doing very interesting things. Gaming, for example, is one place where you can make use of information from the accelerometers, right? I've seen some example games where they make use of the sensors. Like, for example, you can use your phone to, I will show you one example that I implemented myself, where you can use the phone to be able to do things. Like, for example, if you have a ball, you can roll the ball by moving your phone like this. And then you're going to implement a project using accelerometers, right? Anybody else is planning to use accelerometers or sensors, orientation you're going to use, and so on. So that's one thing. Augmented reality is another place where you can very effectively make use of various sensors. Augmented reality including things like, for example, superposing additional information onto what you can see through your camera of your device. Say, for example, you're looking at a tourist skyline, say Victoria Harbour, and then suddenly on the screen you will have labels of all the buildings that you're seeing on your screen being superposed. So that kind of augmented reality. Movement-based interactions, even medical applications, could very easily benefit from making use of information coming in from the sensors. So it opens itself to a lot of interesting applications on your devices, making use of the information from sensors. Now, for sensors, obviously you need to be able to, for example, for orientation and acceleration and so on, from your high school physics, you all realize that the world is expressed in 3 dimensions. And so you always have the x, y, and z dimensions being mentioned for any frame of reference. If you have studied high school physics, you have seen this for explaining motion and so on. So typically at any point on the surface of the Earth, you always look at x and y axes. The x and y axis could be considered as being parallel to the ground. The y axis pointing towards the north in one direction. If the y axis is pointing towards the north, what will be the x axis pointing towards? Towards the east. And z axis or z axis will be vertically in the vertical direction. That's the z axis or z axis. Now, how do you detect changes in the orientation of position of a device? For that, you need to be able to assign axes for your device also. So any device, for example, can be assigned 2 axes. The y-axis along the longer edge of the screen, the x-axis aligned with the shorter edge of the screen, and the z-axis pointing vertically outwards from the screen. So with this kind of assignment, if your phone is resting on the ground like this, why is this interesting? Now this is very interesting because using this information, given any location, you can easily tell the orientation of the phone. Suppose I have a phone like this and I place the phone like this, right? And I know that this is north. Suppose, I don't know which way is north. Let me try to recall. Yeah, this is north. Yeah, indeed, we are facing the right direction. This is north. And my phone has been kept like this on the ground. Can I easily tell whether my phone is properly aligned or not. Right? Now, notice that the y-axis at that point is pointing towards north. So if I look at the ground, the y-axis of the ground or the earth is in that direction, the x-axis is in this direction, and the z-axis is in that direction. So if I put my phone like this here, I immediately know that my phone is not oriented towards the north, but has been tilted a little bit. How do I know how much it has been tilted? I know that on the z direction, it is still in the same direction. So I know that there is no tilt in the z direction, but in the x and y direction, it has been moved by a certain degree. If I'm able to estimate that, I can easily adjust, make use of that information to adjust what I'm doing on the screen. Right? That's one place that it is very useful for this. So for example, on the z direction, so how does my phone know that, suppose I am reading something like this, and then I suddenly tilt the phone like this? How does my phone realize that it's been tilted this way? Because if I am reading like this, my y, x, and z are like this. The moment it changes like this, I know that my axes are tilted. So I immediately know that the orientation has changed, and so I will be able to respond appropriately based upon it. That information is gathered by the sensors in my device. So you can make use of those kind of information to be able to deliver interesting ways of making use of the device. One such device is called as the accelerometer. What does the accelerometer give you? This measures the acceleration forces that are experienced by the device. Acceleration forces. If my device is sitting idle on the ground like this, what is the acceleration it is experiencing? From high school physics, what is acceleration? Rate of change of speed. If my device is sitting idle there, is it experiencing any acceleration? Are you sure? No, that is too much. The device is also rotating with Earth, so that doesn't count. But you know that even if your device is sitting there, it is being pulled towards the ground with a force of gravity, G, right? So the acceleration is reflected in the opposite direction. So by default, an object at rest on the Earth's surface will experience an acceleration of 1g pointing upwards. Unless that acceleration is there, the device will not be sitting without moving there. If it did not experience that acceleration, like for example, if I hold the device there, then you know that it's going to fall down to the ground. So obviously it is not experiencing any force in the reverse direction. If I put it here, the table is exerting a force in the opposite direction. So it is essentially exerting a gravitational acceleration g in that direction. Why is this important? Because if you are going to make any use of the accelerometer, you need to be able to see that in one of the directions, it will always experience that force g. Always. So you need to subtract. Any changes should be reflected with respect to that. So this is static acceleration. So in the computations that you use, by using the information coming in from the accelerometer, you need to take that into account. Okay? Now, if I tilt the device like that, I will be able to see if I tilt if it is like this, with respect to the frame of reference x, y, x, and z, the acceleration g is only acting in the z direction, z direction. But if I tilt my device like this, what happens? The y is still in the same direction, but the x has moved. And my z is now no longer pointing vertically opposite, but my z is pointing in that direction. So the acceleration that is being recorded by the accelerometer will show components in two different values. in the x and the z component, it will show some acceleration. That g force, the g acceleration is now divided between the x and the z component. So by measuring that, you'll be able to see how much tilted the device is. Okay? That's one way you know that you're tilting the device. So that's the reason why this is very useful. The other acceleration is dynamic acceleration. Things like this. You're moving your device. Right? That you know that your device is moving. And for example, the user shakes the device. There is a sudden change in acceleration. You record that the accelerometer is delivering changes in acceleration. And you know that if the user shakes this, if the acceleration changes rapidly for a short period of time, then you perceive it as if that the user is shaking the device. Now, how can you make use of it? Say, for example, you have drawn a picture on the device and you want to erase it. You don't want to go through the practice of rubbing it, but instead, you remember when you were kids, you had this thing called Etch-a-Sketch, where you draw things on the screen. You know, when you were little kids, how would you erase that? You would do something like that. So this one is also like, if you shake it like that, you can erase the screen. How do you know that the user is shaking the device? By looking at the changes in the acceleration. That's one place. Another example of how you can make use of such an effect to provide a user interaction. Say you are viewing photos on your screen, okay? And you want to be able to move to the next photo and the previous photo. One possible way that you can do is to move your thumb, right? I can even do this, right? If I do this, I go to the next photo. If I do this, I go to the previous photo, right? If I do this, I can move back to the albums that are being displayed to select a new album, and so on. See, this is another way of interacting with your device. If you're on the MTR and then you're holding your device, you may not have enough ability to move your thumb on the screen, but this is more easy to do, right? Suppose you get a phone call from somebody that you don't want to answer the phone. You can do that. So basically saying cut off the phone call immediately. You can provide such interaction for the device and so on. So you have to be intuitive to make use of these features. Now, you may say, why do I need to do this? Obviously, when you design an app for your device, if you have been on the market, you realize that there are a million apps on the market. How do you distinguish your app from somebody else's app? You have to provide interesting new features. Some of the interesting new features can easily be afforded by making use of these kind of sensors that are built onto the device. Okay? So, if you check what the accelerometer is returning, that is, you get the information from the accelerometer will return 3 values corresponding to the 3 axes for the accelerometer. If the device is pointing north and resting on the ground like this, the accelerometer should be able to return left hand. Okay? That signifies that the device is at rest. Any change in any one of these parameters can be perceived as the device being moved. And based upon the change in any one of these 3 values, you can approximately calculate how much the device has been moved in any one of these 3 directions. That is very useful as a way of measuring the device's, of being able to know the orientation and the position of the device. A second kind of sensor what is included for motion and orientation sensing on a device is called as a gyroscope. You might have heard about a gyroscope or gyroscope. I don't know how you have been taught this name. In high school physics, somewhere you might have heard about this term. Anybody has heard this term? I don't know what it's called in Chinese, but this is the English name for it. Nobody has heard about this before? Gyroscope, whatever it's called. You have heard about it.
It's used in the Segway.
Yeah, Segway, for example. You know what a Segway is?
Oh,
Have you
yeah,
seen a
yeah.
Segway?
Like-
The two-wheeled thing
Yeah, yeah.
on which you stand and then move around and so on. Similarly, in high school physics, typically a gyroscope, if it is illustrated with a picture there, you would see a person holding a spinning wheel with a hand, on their hand and so on. But what does the gyroscope measure? It measures the orientation of the device. Okay? That's what the gyroscope measures. On some devices, the gyroscope may be included. Most modern, the most recent phones are all including a gyroscope on the device. Some of the older devices don't have gyroscopes. In that case, you don't really need a gyroscope for measuring the orientation. You can make use of the accelerometer and compass readings to be able to measure, to be able to estimate the orientation of the device. I'll show you more about how you can make use of this. So these two, combination of accelerometer and compass, will provide similar functionality as what a gyroscope can do. The third kind of thing is magnetometer. What is obviously, what is a magnetometer? Its purpose. As the name implies, it has something to do with magnetic field. And so this magnetometer basically measures the Earth's magnetic field at any location. How is this useful for your device? Again, that can be used as one way of trying to guess how your device is oriented in the real world. Okay? At any given point on Earth, the magnetic field strength H is between 30 microteslas to 60 microteslas. From high school mathematics, you know what a Tesla is. Tesla is a measure of magnetic field. So that is a measure, if I remember right, it's called a microtesla. So a device that is resting flat on the ground and pointing in the north direction, if you read from our perspective, we don't care what the magnetometer does. From our perspective, we are querying it and it is going to return me three values. Three values corresponding to X, Y, and Z directions. And the magnetometer should return three values, and these three values should be 0, H cos theta, and minus H sin theta, where theta is the angle at which the magnetic field is pointing towards the ground. At every point on Earth, the magnetic field is not tangential to the Earth's surface, but instead the magnetic field is actually dipped by theta degrees towards the north. And that's the reason why these values are those. So if you were to sample the values that your magnetometer is returning, if your device is at rest pointing in the north direction, what should be the values? How can you make use of this in your device? If you have a smartphone, I'm sure many of you have seen a compass app being included on smartphones. Many of you have compass apps on your smartphones? I think I have one on my device. How does the compass app work on this device? How does it know whether it is pointing north or south? It's making use of the information being returned from the magnetic sensor. Okay? From that, you will be able to estimate whether your device is pointing north or east. So using that, you can implement a compass to be displayed on the screen. How do you implement the compass display on the screen? How do you implement a compass display on the screen? Graphics. You can use surface view to implement a compass display on the screen. So if you record a change in any one of these values, then correspondingly calculate how the device has shifted from the north orientation, and then appropriately move the needle on the screen, repaint the screen, the needle in a new position, using surface view, for example. And that's how you implement a simple compass device on your compass application on your device. Okay, so these devices, depending on the kind of sensor that are included, are all going to return some values for you. Now, fortunately, Android provides a very nice interface for you to be able to query the different sensors that are part of your device and then get information back from the sensors. How does Android support sensors in your device? Android framework provides support for various kinds of sensors that are included in your device. Now, not all devices will have all sensors, so you need to keep that in mind. But, for example, within Android framework, it provides several classes in Android that deal with providing you with a method of asking information from the various sensors on your device. The camera class provides you with access to the onboard camera on your device. So if you were to write an application that makes use of the camera on your device, you need to be able to study how the camera class is implemented and then see all the methods of that class, and then use that to get information from your device. Sensor class is a class that represents a sensor. Okay? If you want to know what are the sensors that are included on your device, you can invoke this method called getSensorList, and it will return the list of all the sensors on your device. Now remember that not all devices come with all sensors, so if you're implementing an app assuming certain sensors to be available on the device, the first step would be to query to see whether the device has these sensors. If the device does not have the sensors that you need, then either you try to use the sensors that are available, or if your application does not work with the sensors that are available, you need to inform the user saying this application will not work on your device because you don't have these sensors. So for that, you need to be able to use the sensor class. The SensorManager class is a class that permits access to the sensors that are available within the Android platform. Just like you saw in the previous chapter, you saw Location Manager class. Similarly, in one of the earlier chapters, you saw the Notification Manager class. So in Android, many of these things are implemented by different managers, and sensors are managed by using SensorManager. So obviously, within your application, if you're going to make use of sensors, you need to get a reference to the SensorManager class that is part of your framework. So that's the first thing that you will do in order to be able to access the sensors that are included on your device. Similarly, you might be using the Sensor Event Listener class. What is the Sensor Event Listener class useful for? If the device detects changes in the sensor values, the device should be able, the Android framework should be able to call your app to report the fact that values have changed. Now, how does your app receive this incoming information? For that, you need to declare an event listener. When the application, when the framework calls your application reporting changes, you should be able to receive that. And that is the purpose of the sensor event listener. Just like you saw the location event listener that you used for registering to keep the framework updating you on changes in the location, so you make use of sensor event listener. And sensor event class represents the sensor events and will supply the information, as we will see later. Media recorder class we have seen a little bit earlier. This is for audio, auditory sense. Geomagnetic field is another class that is used for magnetic information. Face detector class. This would be used, for example, for detecting the human face. Now, how is the face detector class useful? You have seen cameras these days come equipped with smiling face detectors, right? Some of the new cameras, when you point to take picture, it can easily detect the people's faces on the screen, and you know whether the person is smiling or not, and then you can, a lot of interesting little features can be implemented in your device, making use of these kind of things. even for your smartphone also such features can be implemented using those. Or if you just want human face recognition, you can make use of those classes. Now, so Android supports different types of sensors. And here is a list of the kind of sensors, if available, they'll be specified. So sensor type accelerometer, refers to the accelerometer sensor, gravity sensor, if it is available, gyroscope sensor, light sensor, magnetic field sensor, pressure sensor, proximity sensor, rotation vector sensor, temperature, and so on. This one returns all the sensors, sensor type 1. Okay, so these are the constants to specify which particular sensor type you are looking for within your application. I'll show you some code to see how you can make use of it. So the sensor type or the sensor class includes orientation, accelerometer, all these different kinds of sensors. Every sensor is also characterized by its accuracy. And accuracy may also be changing based upon the current condition of the sensor. So when the sensor value is returned by your sensor, the sensor even manager may say, this is the value I'm returning to you, but I'm not 100% sure that this is the correct value. So that means that you're reporting unreliable values. So if you, in your app, you don't want to react to a change like that, you can ignore those. But on the other hand, if the sensor is returning a highly accurately identifies saying this is a highly accurate reading of the sensor, and so on. Similarly, another parameter that characterizes sensors is the sampling rate or the refresh rate of sensors. Now, depending on how frequently you want updates to be delivered to your app, you can specify several different levels of sampling rate for sensor. If you are using the sensors for controlling a highly interactive game, then obviously you want the fastest rate to be reported. And this would typically expect updates in 8 to 30 milliseconds duration. This is extremely responsive. But obviously, the more frequently you sample the sensors, the more battery is going to be consumed on your device. So that is something that you need to trade off. You don't want to be exhausting the battery on the device doing too frequent sensings if your application is simply only doing user interface based things for which you really don't need that frequent updates. A second level, which is a little slower than fastest, is called game level sensing rate, which approximately about 40 milliseconds it will deliver a sensor value. If you are using sensors, I would suggest that you, unless you really need this fast updates, try to make use of one of the slower update rates, either normal, which updates every 200 milliseconds. This is more than sufficient for things like screen orientation changes and so on, and user interface, which approximately updates every 350 milliseconds. That is good enough for most user interface events. So this are the different rates at which. So whenever you are using a sensor in your application, you also need to decide what is the rate at which you're going to accept or you're expecting the sensor to deliver results for you. Okay? Now, how do we make use of sensors within the application? Obviously, as I mentioned, SensorManager is the class that is used to provide an umbrella for all the sensors that are included within your device. Anytime you need access to any sensors, first get a reference to the SensorManager and then use the methods of the SensorManager class in order to get information from your device. So the SensorManager basically controls all the sensors that are included with your device. Okay? And if you need to get a reference to the SensorManager, this is how you get a reference to the SensorManager. This is a system service. SensorManager is a system level service, and so you get a reference by including a statement like this within your code. I'll show you an example of an application where we make use of this in practice. Okay? Now, again, as I told you earlier, a particular device may not have all the types of sensors that you might assume to be present in a device. So before you start using a particular type of sensor, you first need to check to see if the sensor is really present on the device. So when you implement applications, that's the first check that we need to do. Is this sensor available on this particular device? We can check the presence of a sensor by using two different methods. You can call this method called as getDefaultSensor, and then specify the kind of sensor that you're looking for. And then this will return whether if the sensor is available. So for example, you can say MyManager. MyManager is the reference that we got in the previous slide by calling the system service here. So if you want to access the accelerometer sensor, you would say MyManager.getDefaultSensor and specify the type of the sensor and the rate at which you want the updates to be delivered. So this specifies. This method will simply return all the available sensors on the device. Okay? You can specify which particular kind of sensor that you're looking for, or you can say sensor type all, which returns all the sensors that are included in the device. These are one of the first checks that you need to do in your application if you're making use of sensors within your device. Okay? After getting an access to any of the sensors, now that you have an reference to SensorManager, you want to be able to receive updates whenever there is a change in the value of the sensor, and that obviously can be done by registering a listener. And this is the method used for registering a listener. Just like Location Manager, where you register listeners for location updates, you can specify the kind of you can specify the listener for this particular kind of sensor. So for example, if you want to be updated every time the magnetic sensor changes, you can specify it by using a method called like this. Say MyManager register listener, and then this specifies the listener code, event listener code. This specifies the sensor. So if you say this as the second parameter, you're saying default sensor for the magnetic field, and then the rate at which you want updates to be delivered. All these three are specific. And so when you supply this, you are registering a sensor event listener. So whenever there is any change in the sensor values, then the sensor event listener is called by the SensorManager. So this is the interface that the SensorManager uses to report the calling application whenever a sensor event occurs, any change in the sensor values. Now this callback interface requires you to implement two methods, two callback methods for this. The first method called as onAccuracyChanged, the second method called onSensorChange. So if there is any change in the value of a sensor, this method is going to be called. So within your app, if you want to be able to respond to changes in the sensor, you need to implement that inside this particular method that you specified, as I will show you with an example. So the onAccuracyChanged callback method is called by the SensorManager. So you obviously are registering the listener to the SensorManager. So when there is a change, the SensorManager will invoke your listener, and this method is called when there is a change in the sensor's accuracy. So if the accuracy value that the sensor is delivering, depending upon the different limits: high, medium, low, unreliable. If it says I'm reporting an unreliable value, meaning that the sensor manager says I don't know whether the value that I'm sending you is correct or not. If in your app you don't want to respond to such values, you can ignore them and so on. So, but this status will be reported. In addition, this method, the onSensorChange method, is called whenever there is a change in the sensor values. Okay? So, if you have registered the listener, if there is a change in the sensor values, this method will be invoked, and that will essentially deliver you the changed sensor values. Okay? And this sensor values, the actual readings from the sensor, are delivered to you in this particular structure called event.values. So if you, for example, if you want to know if you have registered for the accelerometer sensor, you want to know the updated versions of the accelerometer sensor readings, you would use these. And this would contain 3 values for the accelerometer, X, Y, and Z values. Similarly for magnetic sensor, 3 values, and so on. So depending upon the side of the length of the type of the sensor sensor event values will report 3 different values. Okay, 3 elements. If, for example, if the accelerometer, it will report 3 elements representing the azimuth, pitch, and rho, which I will talk about in a minute. Now, how can you make use of this information within your application? Within your device, this is how you might implement an example of a sensors changed callback method. What are we doing here? You're reporting you're looking for an event. When the event is delivered, you say event. So this event, when this method is called, this event object will be returned to you, and then you check for the type of the sensor. So this is how you check for the type of sensor. And if the sensor is a magnetic field, then you're returning the magnetic values. The 3 values will be in this particular array, 3-valued array, and then you read it into that. If it is an accelerometer sensor, that's how you do it. Now, given the magnetic field sensor and the accelerometer sensor values, if your device does not have a gyroscope, then what you can do is you can use these 2 values in order to compute the orientation of the device. Now, Android provides this particular method, which is already built into Android, okay, called as getRotationMatrix. And this particular method, you supply the acceleration and magnetic values that the 2 sensors return to you. If you supply them as inputs, then this method will return 2 values called as rotation mat and inclination mat. These are 2 matrices that it will return. You can then take these 2 matrices and then supply it to this particular method called getOrientation. And when you supply it to this method called getOrientation, it will return the attitude of the device. The attitude represents the orientation of the device. And this orientation is returned in terms of 3 values. This will be a 3-value array. The azimuth, pitch, and rho, the 3 values corresponding to X, Y, and Z. Attitude. So this can be printed by extracting information like this. Okay. These values that are written in attitude is measured in radians. You all know the difference between radians and degrees, right? From high school mathematics. Around a circle it is. If you measure 360 degrees is equal to 2 pi radians. So you need to convert the radians to degrees, and that you can do by multiplying it by this constant called rad degree. That is nothing but 360 by 2 pi, which is the value by degree. And then you can change any radians into corresponding degree. From that, you can know which way your device is oriented at any given point of time. Accelerometer. So this is what I summarize here. Using the readings from the accelerometer and the magnetometer, the SensorManager can be asked to return something called the rotation matrix and the inclination matrix. Now, how do you get these two values? You call this method with these two that we have obtained from the sensors, and then in return, when this method returns, it will return these two matrices called as a rotation matrix and inclination matrix. The rotation matrix corresponds to the rotation to get from the device's coordinate system to the reference world system. So, for example, in this particular case, on this point, if I keep my device like this on Earth like that, then the device's Y is pointing along Earth Y, the device's X is pointing along Earth X, and the device's Z is in the same. So anytime I tilt that, then I know by what value the X, Y, and Z have changed. So that is what is estimated by using the rotation matrix. The inclination matrix supplies the inclination around, right? Magnetic values. So that's the second one that it supplies. Now, given these two pieces of information, we can make use of this other method called as get orientation method. If you supply these two, this method, the rotation matrix, then it will return the orientation. So using the readings from the accelerometer and the magnetometer, the SensorManager can be asked to return the rotation matrix and the attitude vector. Okay? The attitude vector is what enables you to determine the device's orientation with respect to the Earth's axis. This is specified in terms of three values: azimuth, pitch, and roll. What are these three values: azimuth, pitch, and roll? Azimuth rotation is the rotation around world frame z-axis to have the device facing north. So, on the device, if you place the device on Earth, okay? Now, if the device is like this, the azimuth value will tell me around the z-axis how much I need to rotate the device in order to orient the x and y along the x and y of that point. So that is the first one. Along the z-axis, how much I need to rotate the device. So for example, if I put it on the ground, like that, okay, this represents how much I need to turn the device like this in order to orient it towards north and east. So this is the azimuth value. The amount of, so azimuth value tells me how much the device has been tilted in the XY plane. The pitch is the rotation around the world frame x-axis. World frame x-axis. What is the world frame x-axis? This is x-axis, right? So if you need to rotate around the x-axis, this is delivered by this value called as pitch. Rotation around the world frame x-axis to have the device facing straight up along the long dimension of the screen, face up along the line. So this tells me, the pitch tells me how much the device has been rotated in this direction. Okay? That's the third. The third one is roll. Roll tells me how much the device has been rolled in this direction. That's why I have three values: azimuth, pitch, and roll. So by estimating these three, I will be able to tell in which way my device is currently facing. If my device is tilted like this, then I know that the roll value will be not 0. if my device is tilted like this, then I know my azimuth value will be changed. If my device is tilted like this, depending on the way the device is positioned, my pitch value will be different. Okay? So that's what I realized by computing these three values. Now, how is this useful in practice? This is very useful in order to compute some interesting values and be able to control the playing of devices. Now, you remember the ball game that I implemented a long time ago? When we studied the graphics part, and then we were using the left and right buttons in order to move the paddle to deflect the ball back up north. So what I have done is I have taken that same application and I have implemented that same application using the sensors on the device. How do I make use of the sensors? Oops. That's not what it's supposed to be. Okay. How did I make use of those? So what I have done is I have implemented this application where if I tilt like this, my paddle will move left, and if I tilt like this, my paddle will move right. So can you see? Sorry. Hello? Yeah, I'm sorry, I'm in a class at the moment. Can I call you back later? Yeah. I'll be done at 6 o'clock. So can I call you back? Okay, sure. Bye-bye. Sorry. That is not supposed to happen during class. But I wanted to illustrate the game to you, and so the phone was on. So can you see that I can move? Sorry. Can you see that I can move the paddle? Can you see that?
Yeah.
Just by tilting my phone, I can move the paddle. This is hard to show on the screen, but we have a method of doing it. Can you see it? That's very easy to. I mean, it's a lot more easy to play the game using this than using two buttons. That's the purpose. So I have to show it on a real device because that's how you can actually feel this moving. So can you see that this thing is moving like this? So I can make use of it. There we go. You can see this red paddle is moving. The ball hits the paddle before the ball is back. So this is an example of now how do I implement such a feature in the device? Now this particular feature I can implement by simply reading in the sensor values. Now if I need the sensor values, which particular orientation among azimuth, pitch and roll do you think I really need? See, I am not, if I am looking at azimuth tells me how much it is rotated in this direction. That is not going to help me. If I am looking at pitch is telling me how much I rotate in this direction. That is not going to help me. The only thing that is going to help me is if I am changing the roll value. Okay? So that's the only value that I'm going to use from the sensor in order to control the movement of this ball. But suppose I have a ball on the screen and I want to be able to move the ball around on the screen. You have seen games like this, right? You have seen like mazes where you have to move the ball through the maze like this. For that, you need all the three orientations. Any change in any one of the orientations, you need to make the ball slide along that direction. And then if the user holds it like this, the ball slides along that direction. So you should be able to control the X, Y, and Z movement, the velocities of the ball in the three directions by making use of this information. So in this particular case, since my paddle is only moving in one direction, I only need to know the change in the orientation in one direction. So this is what I make use of to implement this particular application. Tomorrow, if you go to the lab, you will be able to see the code. Now, obviously, with sensors, you will immediately ask me the question, I'm using an emulator on my computer. My computer doesn't have sensors, so do you expect me to take my computer and then tilt it like that? It's not going to happen. Nothing is there. Unless your particular laptop is already equipped with sensors, it won't happen. But fortunately, somebody who had plenty of time on their hands wrote a sensor simulator which you can plug into the emulator and then make use of a graphical tool to simulate the movement of the device along the three directions. Okay? This particular sensor simulator code works only in Android 2.3.3 below. It works on Android 4.0 and above also, but it needs some special configuration which I could not figure out in time. So tomorrow you will see the app built for Android 2.3.3 on the device. My mobile phone also runs 2.3.3, so that's why I was able to run. But the code that you write for running on a real device is different from the code that you write using this sensor simulation. Okay? But let me show you first the code that you make use of on a real device. So this particular application, which I refer to as ball game sensor. Now, this particular application, most of the code is exactly the same as the previous example because I just need exactly that. All I need is a way of reading the sensor values and moving the paddle. Previously, I was using these two buttons to move the paddle. Now I use the sensor values to move the paddle. So how do I achieve that? In my main, this particular code corresponds to the version of the code that is implemented for the sensor simulator, which you will see in the lab tomorrow. But for the real application, I give you the code both for the simulator and as well as the real application. If you are deploying it on a real device, you would not be using this version, but much of the features are very, very much the same. So if you are carrying out tests, you can use the sensor simulator within your application also. Now, if you are using sensors, obviously you will be extending the activity and you will have to implement a sensor event listener. Okay? So that's how you register for sensor event listener. In this particular case, within my application, what I do here is that I register for SensorManager here, because obviously unless I register for SensorManager, my SensorManager is not going to return the value for the sensors. Now, if I'm using the simulator, this is the code that I will use. If I'm using a real sensor, this is the code that I will use. So I'm giving you both versions. For the real device, you need to remove this, you need to make some changes up there, and then you need to uncomment this in order to make it work. And then this particular one is needed only when you are making use of a connection to the simulator. If you are using a real device, you don't need that. Now, as you realize, the sensor, what is that? Sensor event listener, obviously you are going to implement the two callback methods for the sensor event listener. So if you are saying you are implementing the sensor event listener, you need to implement these two callback methods, on accuracy change and on sensor change. On accuracy change, I just leave it blank because I'm not really curious about that. But for on sensor changed, this is what I'm doing in the code here. On sensors change, this is going to return the event values. And if I'm using the sensor simulator, I need to access the event type like this. But if I'm using the real sensors on the real device, the code is slightly different. In the lab tomorrow, you will get both versions of the code. Okay? Now, as you see, this one, I just simply read event values. The version of this for the real device is there in the notes that I gave you for this particular chapter. This version is for the sensor simulator. Now, so using this, I extract the acceleration and magnetic sensor values, and then I compute the orientation by using this. I have explained to you how these two methods can be used to compute the orientation. Now, the orientation will return me three values in this attitude. Azimuth, or also named as yaw, Y-A-W, yaw or azimuth. Both mean the same thing. The second one is pitch, and the third one is roll. In this particular case, since I am going to only worry about how this device moves in this direction, I am only interested in the roll. These two are not of interest to me, so I can ignore those two. I will only take this value, and then what do? In this code, what I'm doing is, if roll is greater than 0, then I will move the paddle in that direction. If the roll is less than 0, so this, if my device is sitting like this, this will return a roll equal to 0. If I tilt the device like that, roll will become less than 0. If I tilt the device like that, roll will become greater than 0. So I use that in order to control moving my paddle. As soon as I get the sensor value, if my roll is greater than 0, that means my device is tilted this way, so I need to roll the paddle, I need to move the paddle in that direction. If my roll is greater than 0, my paddle is tilted this way, I move my paddle. Sorry, the other way around. This is greater than 0, this is less than 0. I always get confused between these directions. You can, in your code, you can try both and see which one does it right. First time I implemented the reverse way, and I was moving this and the paddle was just keeping on moving in the opposite direction. Then I realized I should do it in the other way. And so you can do that. So you move the paddle in one or the two directions. By how much amount? That is controlled by how much you tilt the device. So if you tilt the device a little bit, the paddle will move slowly. If I tilt the device like this, the paddle will move very quickly to the other side. That is what I would expect. And that I implement by just taking the roll value and then scaling it down, and then using that as a way of controlling how many pixels I move my paddle to the left or to the right. That's the simple little trick that I'm using for making use of the sensors in order to control the playing of the game. Okay? Now, this also means that I need to implement these two methods, move paddle left and move paddle right, which I have implemented in my DrawView class. In my DrawView class, these two methods are implemented in here. So this is the minor change to the DrawView class that I have done. Right at the bottom, see, this is the code from earlier where we were using the keys to move the paddle left and right. I have added these two methods to move the paddle move right and paddle move left. And these two methods are part of the paddle class that I am implementing. And so that is how I implement a simple application which makes use of sensors to control playing of the game. Okay? So as you realize, making use of the sensors is not that difficult. If you want to be creative in making use of the sensors within your application, this is a very good way of taking advantage of the sensors available within your device. Okay? Any questions before I finish up? Everybody satisfied so far? So that gives you a quick overview of how to make use of sensors within your application. There are many examples that are available online. My example is one such illustration of how you can make use of the sensors. You can think of more creative ways of making use of the sensors for different purposes. Okay. After this, the next chapter, I'm going to deal with networking. Networking not in terms of internet and so on, but networking in terms of how do you connect to a remote server and then exchange information. Similarly, how do you make use of the Bluetooth that is built into your device for establishing connections with other devices in order to exchange information. So that will be the next chapter. After that, we will move on to discussing about web applications, which is one category of mobile applications. And then we'll look at memory management, testing, and other last topics that we will discuss. Okay? So, with this, I will complete this chapter today.